Welcome back to Fact Quest.
Imagine identical twins, Mark and Scott. Mark, drawn to adventure, embarks on a space voyage. His spaceship, equipped with cutting-edge technology, can approach the speed of light. Scott, grounded and contemplative, remains on Earth, his life unfolding at a familiar pace. Years pass, marked by the rhythms of the Earth. Scott experiences the sunrises, the changing seasons, the slow march of time. Mark, hurtling through the cosmos, encounters a different reality. Einstein's theory of special relativity revolutionized our understanding of time. Before Einstein, time was considered a constant, an unchanging backdrop to the events of the universe. But Einstein showed us that time is much more complex and intertwined with the fabric of space itself. It states that time is not absolute, a rigid framework ticking away uniformly for everyone. Instead, time can vary depending on factors such as speed and gravity. This means that two observers moving at different velocities or situated in different gravitational fields will experience time differently. Instead, time is relative, its passage dependent on motion. The faster an object moves, the more pronounced these effects become. This is a fundamental aspect of the universe that has been confirmed by numerous experiments and observations. The faster an object moves, the slower time passes for it relative to a stationary observer. This phenomenon is known as time dilation. For example, astronauts traveling at high speeds in space would age more slowly compared to people on Earth. This mind-bending concept, known as time dilation, is central to the twins paradox. In this thought experiment, one twin travels through space at near light speed while the other remains on Earth. Upon returning, the traveling twin would be younger than the twin who stayed behind. As Mark journeys at near light speed, time itself stretches and bends around him. This stretching and bending of time is not just theoretical, it has practical implications for our understanding of the universe and the potential for future space travel. Imagine Mark's spaceship as a speeding train, hurtling through the vast expanse of space at unimaginable speeds. And now, think of time as the landscape it traverses, a never-ending stretch of moments and experiences. From Scott's perspective on Earth, the train races across the landscape, covering vast distances quickly. He sees the train moving swiftly, a blur against the horizon. But for Mark inside the train, the landscape seems to whiz by at an even faster rate. The scenery outside the window is a rapid, almost dizzying blur. Time, like the landscape, is experienced differently depending on the observer's frame of reference. Each moment is relative, shaped by the speed and position of the observer. For Mark, hurtling through space, time stretches, each tick of the clock slightly longer than for his earthbound twin. This phenomenon, known as time dilation, means that while Mark experiences minutes, Scott might experience hours. This cosmic ballet of time and space reveals the intricate dance of relativity, where the fabric of time itself bends and stretches, creating a unique experience for each observer. Section 4. The turning point, acceleration and time shift. A crucial aspect of the twins' paradox lies in the asymmetry of their journeys. Mark's voyage involves acceleration, speeding up to near-light speed, turning around and decelerating to return to Earth. Acceleration is the key difference between the twins' experiences. It introduces a non-symmetrical element into their journeys through space-time. This asymmetry in acceleration is what leads to the difference in elapsed time. Section 5. Atomic clocks and cosmic confirmation proof in the particles. The twins' paradox, once a thought experiment, has been experimentally verified using atomic clocks. These clocks, which are among the most precise instruments ever created by humans, have allowed scientists to measure time with extraordinary accuracy. By comparing the time kept by two identical atomic clocks, one stationary and one in motion, researchers have been able to observe the effects of time dilation directly. These incredibly precise timekeepers demonstrate the reality of time dilation. Time dilation, a concept predicted by Einstein's theory of relativity, shows that time can pass at different rates depending on the relative speed and gravitational field of the observer. This phenomenon, once purely theoretical, is now a measurable reality thanks to atomic clocks. When flown on high-speed jets, atomic clocks slow down ever so slightly compared to their Earth-based counterparts, confirming Einstein's predictions. This effect, though minuscule, is measurable and has been repeatedly confirmed through various experiments. The difference in time, though fractions of a second, provides compelling evidence for the theory of relativity. These experiments, conducted with meticulous care, provide concrete evidence that time is not an inflexible universal constant. Instead, time is a variable that can change based on speed and gravity. The work with atomic clocks not only validates Einstein's theories, but also opens up new possibilities for understanding the universe and the nature of time itself.